have been discussing in the previous lecture a property of random processes known as Markov property, and this property would enable us to analyze randomly vibrating systems using a different kind of route. So, that is what we are developing. We will quickly recall what we mentioned, what we discussed in the previous lecture. So, Markov property refers to a property displayed by conditional probability distribution functions of random processes. When we say a process is Markov, it does not refer to the nature of probability distribution function. For example, when I say a process is Gaussian, what I mean is that the probability density function has a Gaussian character, whereas Markov property is something to do with memory and not so much about the particular form of probability distribution function. So, the definition of a Markov process for a scalar random process x of t is said to possess the Markov property if the conditional probability distribution function x of Tn less than or equal to xn, that is conditioned on x of Tn minus 1 less than or equal to xn minus 1, so on and so forth, x of T1 less than or equal to x1 is the probability distribution of x of Tn less than or equal to xn conditioned only on x of Tn minus 1 less than or equal to xn minus 1 for any choice of n and for any choice of increasing sequence of T1, T2, T3, Tn. A Markov process with continuous state and continuous parameter is known as a diffusion process. If the Markov process has discrete parameters, then we call it as Markov chain. Mathematically it is easier to deal with Markov chain, but however in vibration problems we need to deal with Markov processes, that is diffusion processes, and diffusion processes have several mathematical pathologies, and we need to take care of some of that when we use these tools. So, we will consider a few examples just to fix the idea. Let theta I equal to 1 to n be an sequence of identical independently distributed random variables, and I define Sn as sum of these theta I from I equal to 1 to n. I can write this summation from I equal to 1 to n minus 1 and write theta n separately, and I can therefore write Sn as theta n plus Sn minus 1. So, from this you can see that Sn depends on Sn minus 1 and theta n is a sequence of independent random variables. Therefore, the probability density function of Sn conditioned on Sn minus 1 is not a function of the observed states, Sn minus 2 equal to S2, so on and so forth, S1 equal to S1, that is Sn is Markov. Also in this case probability density function of Sn conditioned on Sn minus 1 u is actually probability density function of theta n evaluated at S minus u. So, this is by simple rules of transformation of random variables on this equation. Now, when dealing with Markov processes we come across what are known as absorbing boundaries and reflecting boundaries. So, we could explain what these are through some simple examples. So, we will consider now Sn is equal to Sn minus 1 plus theta n. We take that this represents the model for a simple random walk. Now, first example that I would like to consider is an example of an insurance company which starts business with an initial capital of x naught at time t equal to 0. Let y1, y2, yn be the premiums received at t1, t2, tn. This t1, t2 may be days or weeks or months, whatever. Then w1, w2, wn are the claims paid at t1, t2, tn. So, the capital at time n is given by initial capital plus y1 minus w1 plus y2 minus w2 and so on and so forth. So, at any n, if xn becomes negative, that means the capital becomes negative, the company is ruined and it can no longer perform its task, and therefore, we call xn equal to 0 as an absorbing barrier. Okay. So, that means random walk terminates moment that state is the absorbing barrier is reached. So, this is a process with one absorbing barrier xn equal to 0. Now, we will consider another example where two gamblers A and B with capitals A and B play a game n number of times. The game ends when A wins all the capital B from B or A loses all his capital A to B, because gambling cannot continue because one of the person has no longer any capital left with him. So, if xn is capital gain of A at the end of nth game, then x equal to minus A and x equal to B are the absorbing barriers. Here he loses all his capital, here he gains all the capital from player B. So, this is a random walk with two absorbing barriers. Later on we will see when we discuss first passage failures, the barriers can be thought of as absorbing barriers. Suppose x of t is the stress time history, and if x of t crosses say plus sigma y or minus sigma y, suppose if we say that is failure for us, then we can think that as that process as having two absorbing barriers. Another example, daily water level in a dam. So, let B be the capacity of dam in some cubic meters or so, then xn is volume of water in the dam on nth day. Let yn be the inflow on nth day, and if xn here we can say that xn executes a random walk in the interval 0 to b. Either the dam becomes empty or dam is full. If it is empty, it has to wait for inflow. If it is full, there will be a overflow. Whatever is excess overflow on that, I mean excess water that gets stored in the dam gets overflowed. If dam becomes empty, it does not mean that the random walk terminates, it waits for the fresh input. Similarly, if dam becomes full, it waits for the input to stop, so that water level reduces. So, these boundaries 0 and B, we call them as reflecting barriers. So, in contrast with absorbing barriers, if this state is reached, a reflecting barrier is reached, the random walk does not terminate, it can still continue. So, the types of questions that we would ask in this specific context, we can generalize it to problems in structural mechanics in due course. For example, for the problem of insurance company, what is the probability of ruin of the insurance company given its initial capital? Okay. That is time for ruin. Then in the problem of two gamblers, what is the probability of ruin of A and B? Then in the case of dam filling, what is the long term equilibrium probability of water level in the dam? Or what is the probability distribution function of empty periods and non-empty periods? So, these are type of questions that we can answer using tools of Markov process theory. So, these questions have their counterparts in the context of structural reliability, and that we have to slowly appreciate as we go along. Now, some more examples to appreciate what is meant by the Markov property. Now, first example is verify if an IID sequence of random variables form a Markov process. Okay. So, that is we need to verify probability density function of xn conditioned on xn minus 1, xn minus 2, x1, is it this or not, if this statement is true or not. Indeed, it is so because xi's are IIDs, and in fact, it is bit more than that. Probability density function of xn conditioned on xn minus 1 is simply p of xn, because they are independent sequence. So, we can say that this process is Markov. Now, let us consider another random process, x of t is a plus bt, where a and b are IID random variables. Is x of t Markov? I leave this as an exercise for you to show that it is not Markov. Now, an extension of this problem, let us consider a, b, c, d to be 4 random variables. Consider this vector x of t, y of t. Now, this can be written as, suppose x of t is a plus bt and y of t is c plus dt. Question is, under what conditions on a, b, c, d will this vector x of t, y of t be Markov? Okay. So, this again is an exercise that would help you to understand the Markovian properties. We briefly talked about the complete specification of a Markov process. So, we will start with first order probability distribution function. So, probability distribution at t equal to t1 is probability of x of t1 less than or equal to x1. Now, at 2 time instants T1 and T2, the probability x of T2 x1 x2 colon T1 T2 would be probability of x of T2 less than or equal to x2 intersection x of T1 less than or equal to x1. That joint probability is actually x of T2 less than or equal to x2 conditioned on x of T1 less than or equal to x1 into probability of x of T1 less than or equal to x1. So, this is known, therefore, for complete specification I need this also. Suppose if I take 3 time instants T1, T2, T3, then I can write the joint density function in terms of a sequence of conditional probability distribution functions. First is x of T3 less than or equal to x3 conditioned on x of T2 less than or equal to x2 intersection x of T1 less than or equal to x1 into x of T2 less than or equal to x2 conditioned on x of T1 less than or equal to x1 and into probability of x of T1 less than or equal to x1. But since the process is Markov, the first of these terms x of T3 less than or equal to x3 is independent of x of T1 less than or equal to x1. So, I simply write this as this and this is multiplied by the next conditional probability distribution and the first order probability distribution. So, this I can write it as product of probability density function probability of x of T nu less than or equal to x nu conditioned on x of T nu minus 1 less than or equal to x of nu minus 1 into the first order probability distribution function at t equal to T1. This nu takes value from 2 to 3. If you now consider n time instants, we can show that using a similar logic, this is equal to product of n transitional probability distribution functions into the first order probability distribution function at t equal to T1. So, the complete specification of a Markov process therefore is in terms of the transitional probability distribution function and the first order probability distribution function for all n and for all choices of T nu running from 1 to n. Or alternate to this would be to specify the second order joint probability distribution function for all n and for all choices of nu running from 1 to n. If you know the second one, you can easily deduce the first one, and if you know the first one, that is if you know this transitional density function, probability distribution function and this probability distribution function, first order probability distribution function, you can deduce the second order probability distribution. So, both are equivalent. So, this joint density function, as I said, we are writing it as product of this transitional probability distribution function. So, this transitional probability distribution function we call it as TPDF. I use uppercase letters TPDF following the convention that I am doing. For distribution functions I am using uppercase letters and for density functions I am using lowercase letters. Now, this transition probability distribution function represents the evolution mechanism of a Markov process. So, you start with first order probability distribution at t equal to T1 and go on multiplying these TPDFs to get the joint densities at the time instance that you want. So, this is the evolution mechanism. Now, just to give a verbal description, we can consider probability distribution function at Tn plus 1, Tn and Tn minus 1. Suppose we interpret n plus 1 as tomorrow and n as today and n minus 1 as yesterday. What Markov property says is tomorrow's happenings depend on what is happening today and not on what happened yesterday. That means it has one step memory. If time is measured in units of days, this is the property, Markov property. So, you should recall that for linear dynamical system, future evolution depends upon initial conditions and not how initial conditions have been arrived at, right. So, what that means, if you consider now dy by dt as a deterministic ordinary differential equation, a vector differential equation, dy by dt is h of y of t comma t with some initial condition at t equal to 0 provided. Now, if you take 2 time instants t2 greater than t1, y of t2 if we denote that solution as q of t2 y of t1 comma t1, this will be the nature of the solution. That means, y of t2 depends on y of t1 and t1 and of course t2 and not on how y of t1 has been arrived at. So, that is solution at t2 depends on y of t1 and not on y of tau for tau running from 0 to t1. So, Markov property can be viewed as the stochastic analog of the above property of ordinary differential equations in the context of deterministic systems. Now, we have defined the transitional probability distribution function. I can define the associated probability density function by differentiating the probability distribution function. This is a straightforward definition. So, lowercase p of x nu semicolon t nu conditioned on x nu minus 1 t nu minus 1 is the partial derivative of the TPDF probability of x of t nu less than or equal to x nu conditioned on x of t nu minus 1 is equal to x of nu minus 1. So, the nth order probability density function, you can see through this logic outlined here. We start with the nth order joint density function and write it as a sequence of conditional probability density functions and use the Markov property, and we can show that the nth order probability density function can be expressed in terms of the first order probability density function at t equal to t1 and product of these TPDFs at t nu, t2, t3, t4, t5 up to tn. So, this is quite similar to what happened with probability distribution functions. Again, we can see that complete specification of Markov process can now be in terms of first order probability density function and the transitional probability density function. So, that is what Markov process is also completely specified in terms of transitional probability density function and the first order probability density function for all n and for all choices of t nu. This is very important that it should be true for all n and all choices of t1, t2, t3, tn. Since the transitional probability density function and first order density function can also be derived from a second order probability density function, a second order probability density function for all n and for all choices of t1, t2, t3, tn is also a complete specification of Markov process. So, we can again emphasize the multi-dimensional probability density function which is needed for complete specification of a random process is obtained in terms of the initial probability density function and product of transitional probability density functions which represents the transition mechanism. Now, if a process is Markov, the transition probability density function need to satisfy certain internal consistency conditions. To illustrate that, we consider 3 time instant t equal to t1, t equal to t2 and t equal to t2. So, t1, tau and t2, so that tau is greater than t1 and t2 is greater than tau. So, now we consider the joint density function between t equal to t1 and t equal to t2, that is x2 comma t2 semicolon x1 t1. This can be written in terms of probability density of x2 comma t2 conditioned on x1 t1 into first order density function. This can also be viewed as the marginal density function of the joint density function between the random variable here and random variable here with respect to the states at t equal to tau. Now, I write this 3 dimensional joint density function in terms of conditional density functions as shown here, and then express this conditional density function of x2 condition on t2 condition on what happens here and what happens here. I write this integral in this form, and if I use now the Markov property, this becomes here this p of x1 t1 and p of x1 t1 here gets cancelled, and I will do 2 things. For LHS I will write this, and on the right hand side I will use Markov property and get this relation, that is probability density function of x2 comma t2 condition on x1 t1 is given by the integral of x2 comma t2 condition on x comma tau, which is the intermediate time instant, into probability density function of x of tau condition on x1 t1 dx. This should be true for all t1, t2 and tau. So, this is this can be viewed as a kind of a compatibility or consistency condition for the process to be Markov. Now, this forms the basis for actually analyzing vibrating systems and deriving the equation of motion for the probability density function. So, the big picture that we should bear in mind at this stage is to answer this question, that is how to utilize this result in characterizing response of randomly driven dynamical systems. So, this is our agenda, we should keep that in mind when we get into some of these details. Now, we talk about what are known as random processes with independent increments. Now, let x of t be a random process with continuous state and continuous parameter time. I consider increasing ascending sequence of time t1, t2, tn, we consider these n time instants, and this defines the n random variables x of t1, x of t2 and x of tn. Now, I define another random variable x of t1 comma t2 as x of t2 minus x of t1. This random variable is called the increment of x of t on the interval t1 to t2. Now, for given time instant t1, t2, tn, we can also form a sequence of increments which are again random variables x of t1 comma t2, x of t2 comma t3 and so on, x of tn minus 1 comma tn. This form a sequence of independent random variables. If this sequence of increments form a sequence of independent random variables, then we say that x of t is a process with independent increments. Okay, that is the definition of a process with independent increments. Now, let x of t be a random process with independent increments. Now, I define y of t as x of t minus x of 0 with t greater than or equal to 0. Now, y of t is a process with independent increments and also has a property that probability of y of t equal to 0 is 1, because y of 0 is x of 0 minus x of 0, which is 0. So, y of t equal to 0 has probability of 1, okay. And also y of tn minus 1 comma tn is nothing but x of tn minus 1 tn, okay. If you write say y of tn minus 1 comma tn, it is y of tn minus y of tn minus 1, y of tn would be x of tn minus x of 0 and y of tn minus 1 will be y of tn minus 1 minus y x of 0, and that would get cancelled and it will be same as x of tn minus 1 comma tn. That means y of t has all the properties of this sequence except that at t equal to 0 probability of y of t equal to 0 is equal to 1. So, therefore, the point is without loss of generality we can always take p of x of t equal to 0 as 1, okay. So, if it is not true, then we can make this transformation and deal with the process y of t, okay. Now, the important feature of process with independent increments is that such processes have Markovian property. Now, to see that, let us define y of t equal to x of t if probability of x of 0 equal to 0 is 1, otherwise x of t minus x of 0 if this is not equal to 1. In any case y of t naught will be 0 where t naught is 0. Now, we consider the sequence tn greater than tn minus 1 etc. t naught, and t naught is 0, and the associated random variables y of tn comma y of tn minus 1 and y of t1. Y of tn can be written as sums of these increments y of tj minus y of tj minus 1. You can substitute and verify that it is indeed true. That means y of t1 minus y of t0, y of t2 minus y of t1 etc. etc. It will be left with we will be left with only y of tn. Now, we denote zj as y of tj minus y of tj minus 1. These are sequence of independent random variables. Now, this y of tn therefore can be written as zn plus y of tn minus 1. So, this is in the form of a simple random walk, and we already showed that simple random walk has Markovian property, therefore, y of t is Markov. You can see here y of tn depends on y of tn minus 1, and the change from tn minus 1 to tn is caused due to zn, and zn, z1, z2, z3, zn are all independent random variables, therefore, y of t is Markov. Now, till now I have been talking about sequence Markov property of scalar random processes. Now, we can generalize this notion to vector random processes. So, if x of t is a vector random process with continuous state and continuous parameter time t, let us consider such a random process. Again we consider the time sequence t1, t2, t3, tn, the n time instants and the associated random variables x of t1, x of t2, x of tn. X of t1 is a vector of random variables, x of t2 is a vector of random variables, okay. So, the vector process x of t is said to possess Markov property if nth order conditional joint probability distribution function of these vector random variables x of t n less than or equal to x n conditioned on these events is given by probability of x of t n less than or equal to x n conditioned only on what happened at t equal to n minus 1. And if this is true for any n and for any choice of t1, t2, t3, tn, we say that the vector random process x of t has Markov property. This is a straightforward extension of the definition for a scalar case. Suppose if you consider, just to elaborate this notion a bit, the m dimensional vector random process x of t, x of t1, x of t2, x of t is said to be Markov if the probability of intersection of I equal to m xj of Tn less than or equal to xj, which is nothing but the probability distribution function conditioned on these events where x of t1, x of t2 here are all vector random variables, and this depends on only the state at t equal to Tn minus 1, then we say that x of t is Markov. So, this quantity we call it as the transition probability distribution function for the vector random process x of t. Associated with this, we can derive the transition probability density function for the vector random process x of t by carrying out the m time differentiation of this transition probability distribution function. Okay, this is a straightforward extension of the notions that we have used in scalar case. Some remarks should be made at this juncture. A component of a vector random process would be a scalar random process, but that need not have Markov property. A vector of a vector random process could be Markov, but the components of such a Markov random process need not be Markov. We will see that in due course again. Now, different components of a Markov vector random process could be differentiable in the mean square sense to different levels. A Markov process itself is not differentiable. I will clarify this what these things mean in due course, but we should make notes of this at the outset. If a vector random process has independent random increments, that is vectorially, the components of the random process need not have independent increments. So, you need to think about it and verify by actually working out what exactly these statements mean. The Chapman-Kolmogorov-Smolchowski equation, that is a consistency equation, can be generalized for the vector random process, and the mathematical form of that remains identical, except that now we are writing joint probability density functions instead of scalar probability density functions. So, that means the probability density function of x3 tilde conditioned on x1 at t equal to t1 is given by this product of these two TPDFs integrated over y1, y2, yn. So, this is the condition for internal consistency of a vector Markov random process. We could generalize the theory of Markov process in a slightly different way. Again, let us return to a scalar random process. Let x of t be a scalar random process with continuous state and continuous parameter time t, and again we consider n time instants and the associated n random variables. Now, x of t is said to possess second order Markov property if probability of the event x of t n less than or equal to t n the event x of t n less than or equal to x n conditioned on these events depends upon what happened during t equal to t n minus 1 and t equal to t n minus 2. If this is the property that the probability distribution satisfy, then we say that x of t is Markov with second order. So, this notion can be generalized to higher orders. This I am mentioning for sake of completeness. Now, one more thing that we will be talking about is Markov process with stationary increments. Now, x of t is said to be Markov process with stationary increments if you consider the TPDF, suppose you consider 2 time instant t1 t2 and other two time instants t1 and t3. That means I shift this t1 t3 by a fixed amount tau. That means the distance from A to B is t3 minus t1 and distance from C to D is again t3 minus t1. That means there are now two random variables here separated by t3 minus t1 and there are two more random variables separated by the same distance t3 minus t1. So, if we now consider the transition probability density function from say A to B and C to D, and if it is a function of only tau, then we say that the process has stationary increments. Okay. So, TPDF from A to B is same as TPDF from C to D. Okay. So, in such a situation the TPDF can be simply be written as P of x3 colon tau conditioned on x1, where tau is a transition time, and as tau goes to infinity the transition PDF now depends only on tau x3 semicolon tau, and the memory of x1 is lost, and this is one of the properties that we need to use. So, stationary Markov random process is completely specified in terms of the TPDF in this case, because at tau tends to infinity it is defined only in terms of the transition probability density function. You should notice that x of t, if x of t is stationary, x of t has stationary increments, but it does not mean that if x of t has stationary increments there is no this statement need not mean that x of t is stationary. So, you can again verify. These are small points that would help you to understand the notion of stationarity and stationary increments. Now, our basic interest in using Markov property would be to derive an equation for evolution of the probability density function. So, how do we go about doing that? This equation is known as kinetic equation. So, let x of t be a scalar random process and Px of x semicolon t be the first order probability density function of x of t. So, Px, this PDF depends on two variables x and t. Can we derive a partial differential equation which describe this evolution in x and t? That is a question. Okay, how can we do that? If we can do that, x and t would be the independent variables and the dependent variable will be the PDF. Thus, the differential equation that we are looking for would be a partial differential equation with p as dependent variable and x and t as independent variables. Furthermore, can we also derive the partial differential equation governing the n dimensional joint PDF of x of t? If we can do it for one dimensional PDF, you may think of doing it for n dimensionals. So, from now onwards what I will do is this p x of x comma t, I will simply write it as p of x colon t. This subscript x of t I will omit for sake of simplicity. This is a reference that you may find useful for the topic that I am going to cover in this part of the lecture. Okay, how do we proceed? Now, let us consider two random variables x of t and x of t plus delta t. So, the probability density function at t plus delta t can be obtained as the marginal density of the joint PDF at t and t plus delta t. This is a simple statement. This itself can be expressed in terms of product of a conditional probability distribution density function and a first order probability density function. Now, let us define the increment delta x of t as x of t plus delta t minus x of t. Let us consider the conditional characteristic function of delta of x of t conditioned on x of t being equal to x prime. So, that would be expectation of I u delta x of t conditioned on x of t equal to x prime. Now, let us denote this as phi u comma t plus delta t conditioned on x of t equal to x prime. So, this is actually the expectation, and in terms of the density function it is given this is a definition of the characteristic function, where this delta x of t is x of t plus delta t minus x of t such that delta x is x minus x prime. Now, we will do some manipulations on this. if this is the definition of characteristic function, the conditional PDF can be obtained by inverting this through using inverse Fourier transform. So, I get this equation. Now, the integration is with respect to u. Now, you recall f of x plus h can be expressed in terms of Taylor's expansion in this form that we will be using. So, now let us expand the characteristic function around origin u equal to 0. So, I will write phi u comma t plus delta t as 0 plus u t plus delta t etc., and then expand this around the origin u equal to 0, and if we do that we get this expansion, and we know that through the property of characteristic functions this is nothing but the moments of the random variable. So, in this case we are talking about delta x condition on x of t equal to x prime, and I get this as delta of x n, expectation of that. Now, quick recall, we know the definition of a characteristic function of a random variable is the expectation of e raised to I omega x, and phi x of omega is actually the Fourier transform of the probability density function, and we have shown that the characteristic function has this property which I am using in fact, and the inverse Fourier transform is given in terms of this, and that leads to definition of probability density function. Similarly, we can define characteristic function for a random process. Suppose if you consider n random variables x of t1, x of t2, x of tn, I can write the expression for the joint characteristic function of these n random variables through this expectation, and that is nothing but this integral. Here this u1, u2, u3, un are all real valued, and the moments x of t1 to the power of j1, x of t2 to the power of j2 etc. can be obtained in terms of the derivatives of this characteristic function evaluated at the origin following this rule. Okay, this is the extension of the definition of characteristic function for a random process. So, the red font I am using to recall what we have already done. So, these are things that we are recalling. Now, let us go back and write in the expression for the inverse Fourier transform of the density function the expansion that we have used, and we get this this expression, where this quantity an x prime comma t is this moment delta xn of t conditioned on x of t equal to x prime, and these are known as incremental moments. So, in terms of incremental moments I have got now the expression for this probability density function. Now, I need to redesign this expression, recast this expression slightly in a different way. So, for that we recall if you take the Fourier transform of a direct delta function, we get a constant. So, a direct delta function therefore can be expressed as inverse transform of e raised to minus iux as shown here. Now, if you differentiate this, it can be expressed in terms of differential of the on the right hand side. So, we get this expression. So, what we are getting here turns out to be related to the derivatives of direct delta function, and we can use that result here, and we get this expression. Now, a slight amount of rearrangement of these terms and splitting so we have substituted in terms of direct delta function, and we return now to the first order density function. This is the integrand. So, this expression will come in the integrand, and I get this expression, and again rearranging these terms and using this fact that nth order derivative of integral like this is nothing but dn dx to the power of n f of a, and if we do that I get this expression. This derivation is bit tedious, but I am trying to highlight some important steps. So, you need to work through this bit patiently, then only you will follow this. So, what we do now is the summation on the right hand side. I will write the first term that is n equal to 0 separately, and then take the summation from 1 to infinity. So, in this I get this expression a naught x comma t, and this is nothing but delta x to the power of 0 of t conditional on x of t equal to x prime, and this is 1. Now that would mean I can take this to the left hand side, and now I am in a position to define the derivatives. I will divide this by delta t and take limit delta t to 0, and on the left hand side I get dou p by dou t, and on the right hand side I get these expressions which can be simplified to get a partial differential equation as displayed here. So, this is what I am looking for. This is actually the evolution of probability density function of x of t in terms of what are known as incremental moments or derivative moments as shown here. We can call this right hand side, that is we take dou by dou x outside and call the what remains, that is n equal to 1 to infinity minus 1 to the power of 1 divided by n factorial and n minus 1 derivative of this as lambda of x comma t. Then this equation can be written as dou p by dou t plus dou lambda by dou x equal to 0. So, this takes a quite a elegant form now. So, this can be viewed as equation of conservation of probability. So, this is similar to the equation of continuity in fluid mechanics. So, this is a diffusion equation, and this quantity lambda of x comma t can be interpreted as amount of probability crossing x in unit time in the positive direction. So, there is an analogy with fluid mechanics that would be helpful. But this equation, although it has this nice form, if you look back, this lambda itself has terms running from n equal to 1 to infinity, which has derivatives to the power of n, where n is running from 1 to infinity. So, that would mean that this equation has infinite order respect to the spatial coordinate, and therefore, it is not a partial differential equation which can be solved. It is only a formal representation. But there is one nice result which would help us to simplify this, and that is what I will briefly mention. What this result says is, if the derivative moment alpha n exists for all n and is 0 for some even n, then it automatically means alpha n is 0 for all n greater than or equal to 3. What that means is, this differential equation has infinite number of terms. If it is going to have finite number of terms, it has to stop at n equal to 2. There cannot be an equation which is valid for n equal to 5, 7, etc. If it is not 2, it has to be infinity. There is nothing in between. Okay, right. So, there exist two cases of this continuity equation, the one in which the order of the equation in x is infinite and the other in which the order is 2 or less. We would be interested in applying the kinetic equation for the case where this alpha n equal to 0 for n greater than or equal to 3, and we will show that for a Markov process that is indeed true. Okay. Now, there is a brief proof for this. I will just highlight the steps so that you could go through a bit more carefully. So, if the derivative moment alpha n exists for all n and is 0 for some even n, then alpha n x comma t equal to 0 for n greater than or equal to 3. So, let us consider the case where n is greater than or equal to 3 and let n be odd. So, alpha n x comma t is actually this expectation, and I can write this as product of this quantity inside the bracket to the power n minus 1 by 2 and n plus 1 by 2. If you multiply this, you will get this term. Okay. Now, this is a permissible splitting. On this now I will apply Squarce inequality. You recall Squarce inequality we used to show that correlation coefficient is between +1 and -1 earlier. The same inequality I am using. I will get alpha n square x comma t must be less than or equal to product of two expectations, that is alpha n square x comma t must be less than or equal to product of alpha n minus 1 x comma t, alpha n plus 1 x comma t for n greater than or equal to 3 and n odd. For n even, we can show that we get another similar inequality. Now, if you carefully consider these two inequalities, you can show that if alpha n is 0 for some n greater than or equal to 3, then all alpha n should be equal to 0. So, let alpha r x comma t equal to 0 where r is an even integer. So, let n equal to r minus 1, r plus 1, and using this we get these two inequalities for r greater than or equal to 4 and r greater than or equal to 2. Similarly, we get for n r minus 2 and r plus 2 using for n even we get these two inequalities, and if I put all of them together I have these 4 inequalities. Now, in illustration, let alpha 3 be 0 and alpha n exist for all n. So, now you can use these inequalities in sequence and show that if this is true, alpha 4 must be equal to 0 and alpha 5 must be equal to 0. If r 4 and 5 are 0, 6 and 7 must be 0. If 6 and 7 is 0, 8 and 9 must be 0. So, you can show that all n greater than or equal to 3 would be 0. So, that is constructed here, and this requires some moment of reflection. There is no complex issue here. You have to simply understand what is being said through these inequalities, and if you appreciate that, we would have proved the statement that we made, that if alpha n greater than or equal to n greater than alpha n for n greater than or equal to 3 is 0. No, what is the statement? This statement is if the derivative moment alpha n exists for all n and is 0 for some even n, then alpha n is 0 for all n greater than or equal to 0 for all n greater than or equal to 3. If that is the case we are considering, the kinetic equation now becomes a simpler equation, diffusion equation. Dou p by dou t is minus dou by dou x alpha 1 into p plus half dou square by x square alpha 2 into p. This equation is known as Fokker-Planck equation. Here this lambda is expressed in terms of alpha 1 and alpha 2, and the initial condition for this this equation would be that at t equal to 0, x of 0 can be a random variable and its probability density function is specified. Now, boundary conditions, different possibilities exist. I mentioned about absorbing barriers and reflecting barriers and so on and so forth. So, there is a body of literature on what are the admissible boundary conditions and when do solutions exist, etc., etc. So, I will not be getting into all those details. Now, if x of t takes values from minus infinity to plus infinity, as in the case of say a Gaussian random process, then boundary conditions are to be specified at plus minus infinity. These boundaries are inaccessible. So, if we now consider the kinetic equation and integrate from minus infinity to plus infinity, we can manipulate this expression a bit, and we know that P of area under the probability density function is 1, therefore, the first term would be 0, and that leaves us with the condition that dou lambda by dou x into dx must be equal to 0. This requires lambda of minus infinity colon t must be equal to lambda of infinity colon t. A stronger condition would be that these two are independently equal to 0. A much stronger condition would be that the probability density function itself is 0. So, this we can show that corresponds to an absorbing boundary and this corresponds to a reflecting boundary. If x of t can take values only in the bounded region x1 to x2, then the Fokker-Planck equation is valid in this region with you have to manipulate this equation again from, if you integrate from x1 to x2, we get this condition, and a stronger condition would be this, and a much stronger condition is this, and as I was mentioning this boundary condition corresponds to reflecting boundaries, and this stronger condition corresponds to absorbing boundaries. Now, if alpha n are independent of time, stationary solutions might exist such that dou p by dou t becomes 0 as t goes to infinity, and one gets the simplified equation which is there is no time variable. This is in fact an ordinary differential equation which leads to the solution lambda of x equal to 0. So, this is one way to find out steady state solution. Now, the generalization of kinetic equation for a case of vector random process is quite straightforward conceptually, but it is a bit tedious to express, but I leave that as an exercise. This will be the form of the kinetic equation. Here now I get the derivative moments in a slightly more involved manner, and this is reflected here. So, till now what we have done is we have derived the governing partial differential equation for the evolution of probability density function. Now, the question that we should be answering is to set up this kinetic equation. For example, if we want to set up this equation, I need to determine these parameters alpha 1 and alpha 2. Suppose I look at a dynamical system and I formulate its equation of motion. Starting from that, can I derive alpha 1 and alpha 2 in terms of, for example, mass, stiffness and damping properties of the system? Can I derive these derivative moments? I will explain how that can be done in the next lecture, but if that can be done, then this equation that we are seeing here can be thought of as the equation of motion for the dynamical system, with dependent variable being the probability density function. We have derived till now the equation of motion for the samples of a random process. From that we could derive the mean, the covariance, etc. Now, can we derive the equation of motion directly for the probability density function itself? If that is so, how do we relate this equation to the governing differential equation of motion for a dynamical system? If we derive this equation, the next question would be on the associated initial conditions, the associated boundary conditions, what are admissible and when do we hope to get a solution. The next issue would be how can we solve this equation. So, it turns out that for linear dynamical systems with additive Gaussian white noises, this differential equation can be solved exactly. Not just that, but that is not a major use of Markov process theory. The Markov process theory becomes quite useful because this equation of motion can be derived even for nonlinear systems, for cases where there are non-Gaussian excitations, for cases when the excitations are parametric. There can be parametric excitations and external excitations simultaneously acting on the system. This forms an avenue for formulating the governing equations of motion for the probability density function. And under certain situations, the governing equations even for nonlinear systems and even for parametrically excited systems can be solved exactly. So, the Markov process approach provides a means for obtaining exact solutions for certain class of nonlinear random vibration problems. It also provides a strategy to formulate approximate methods when such exact solutions are not possible. So, this is what is the essence of Markov vector approach, and in the next lecture we will consider some of these questions in greater detail, and we will conclude this lecture at this juncture.